But there is a problem with that method, and I'm trying to illustrate that in a few minutes. It doesn't scale properly with the size of the system. So how much of the electron correlation energy, or correlation energy you get, actually depends on the system. The larger the system, the less you get. Why is that? Let's look at, and that's called the size extensivity problem. Extensivity problem. Sometimes also called size consistency problem, and there is a difference between the two. Never mind here, just get the idea. If we look at, let's take the simplest problem, we take H2 in CISD, and that actually is what we did on Tuesday. Remember that minimal basis set H2 discussion I had? We ended up, in order to solve the dispersion problem, we ended up with a combination of two determinants. One was a Hartree-Fock determinant, the other one was a doubly excited determinant. And the single excited I didn't include because it only did correction. So actually I was doing CID with you, or CISD. So if I have H2 alone and CISD, then I'm going to have double excited determinants included there. But if I now take another system, if I take two H2 molecules, and let's take them in the simple case that they are infinitely apart. At a very large distance. What do you think should the energy be of, in this case, if I have a dimer of H2, but they are infinitely apart?
Twice the energy with bond.
That should be twice the energy of one H2. And if you have intermediate distances, it should be sort of approximately. At least, I mean, it should, if I add more and more H2, the energy should sort of scale properly. It should increase in the number of systems we have. But now look, I have, let's take our minimal basis set H2 system from Tuesday, where I have a sigma G and sigma U orbital. Remember that, sigma G, sigma U. I have, of course, in a CISD, I have my Hartree-Fock determinant, and I have that determinant. That's a double excited determinant for H2 alone. Now, if I have infinitely, there's infinite distance between them here. I have the other H2. In order to get this one, in order to get twice the energy, of course the other H2 molecule also should be allowed to have its double excited determinant included in the calculation. That's also double excited determinant on this. But if that is now part of one calculation, I make sort of a supermolecular calculation, what kind of excitation is that? Emil?
That's a quadruple.
That's a quadruple excitation. Both together is a quadruple excitation. But I'm only doing CI singles and doubles. So this excitation, this determinant, is not going to be in my wave function here if I do the dimer. I'm going to have this or this. But I'm not going to have both together. So I haven't included all the determinants which would be necessary in order to describe the dimer at the same level as I described the monomer. So these methods cannot scale properly because I'm going to treat the smaller system, here the monomer, always better than I'm going to describe the dimer, trimer, whatever, and the large system. There are ways to correct for that, and there's sort of what is called a Davidson correction to CI single doubles, which essentially is just including this one on top of it. Not all quadruple excite, because in principle, well, for H2 I can't make a quadruple excite, but if I have a system with 4 electrons, then I could have a quadruple excited determinant also for the monomer. But if you do this quadruple correction, then you sort of include this kind of quadruple excitations.